Hello my dear students, now we have to observe a 3-point sine wave oscillator circuit, but in this kind of circuit there are a lot of sine wave oscillator circuits, but they want to, in that particular experiment they want LC oscillator waveband working. So for LC oscillator I have to take in that oscillator section I have to take, there are a lot of oscillators, Wine Bridge oscillator, and there are Collpitts oscillator, Hartley oscillator, Robinson oscillator. A lot of oscillators are on. We have read on theoretical background, but the main thing is that for LC oscillator I have chosen the simple Collpitts oscillator. There is the L and the C, and there are two capacitors, one inductor, the LC Collpitts oscillator that I have used here. So that is the circuit diagram of the Collpitts oscillator or LC oscillator. We have used here 2N quadruple 2A transistor, and there is a DC bias voltage that I have to give here for self-biasing the transistor, and for that DC voltage in that there is the emitter section. In that emitter section output we will get the sinusoidal or oscillating output. Okay, let's start. Then how we could start the oscillation criteria, and there is the R2, it's 1 kilo ohm. We have taken the 1 kilo ohm, and for that this table should have to be filled up. So for to finding out the VTP4 we have to find out where this oscillation will start and stop oscillation, and oscillation amplitude to its maximum, and there is an IEO, and that should be found out by the emitter voltage. As you can see that emitter section we have the output is in the emitter section. So emitter voltage divided by the R11, that means the 1 kilo ohm the output resistance. But how could you find out the IEO in that particular section? First of all, you have to keep on your mind that is there is a starting oscillation where the oscillation starts in this type of two currents. You can measure it or you can find it out. So that is the table. There is a similar data table here and there. You can use any of them. That's not the factor that this should have to be there. Sorry, so there is similar to that. Okay, it's not the 5.2 table. There is another 5.2 table. Just you have to just fill up this table in that particular section. So both are the same. So just we have to record this lowest and highest frequency. We have to after taking the table 1, we will go to the table 2 as frequency data, that is the frequency data record table, to find out the maximum frequency and the minimum frequency in that particular oscillation. Okay, let's start. And the simulation starts. Now I can see that there is an AC or alternating current voltage here, and we haven't used any kind of AC voltage all around. Just DC voltage has been used. So just to stop it and find it out that in the grapher section how that oscillation begins. Okay, let us just put over the output voltage and start simulation. Okay, so I have to use some techniques to find it out clearly. Okay, just in this simulation the zoom all voltages, and just taking again we should run and find out that. Again just run it, and then there is a time division factor in the oscillation. Just widen the division, just to widen the division. You shouldn't, just widen the division as much as you can. It's 1 microsecond per division. Okay, just quite a bit wide. You can make it wide too, 500 nanoseconds per division, and then we should stop the simulation right now. Now we will get the peak to peak voltage in that particular section. Here you can see that there is a 6 volt upper limit section, because we have used the 6 volt in DC, but the shift has been made by from 0 to 6 volt, but that's not the shifting, that's not the peak to peak voltage right now. But if you want to find out the peak to peak voltage, there is the peak to peak voltage, that is 5.9449 voltage, and that is the last portion is the 279.82 millivolt. So we have to calculate the peak to peak voltage. Now what is the, where the oscillation starts, and oscillation amplitude to amplitude to its maximum. Okay, so you have to put the maximum value. The maximum value here is almost 5.9466 volt, and that will be 5 point, put the cursor here, 5.9466, 946666, and that's voltage, not millivolt. And for that particular region voltage, you have to find out the current. There is certainly there is a equation to find it out, but I would rather, taking the equation, I will go to the schematic section and use an ammeter to find out the current. Okay, to use an ammeter to find out the current. Okay, just we have to use an ammeter. Okay, it's a voltage probe, so you have to use it. Okay, just put the value of 1 kilo ohm, divide the value the highest value to the 1 kilo ohm. After dividing 1 kilo ohm, the IO will be 5.9466, 5.9466 milliampere, and that's the volt here. And if you want to find out the starting of starting oscillation, where the oscillation starts, the starting point of oscillation and stopping point of oscillation. The starting point of oscillation are quite like that. Just take the value, go to the splitting section, stop the simulation, take the highest point, that is the highest point of 5.9466 right now, and that is the lowest point will be where the oscillation stops, that is the 278.60 millivolt. So that will be the same thing, and the lower point is maybe 285.90. Okay, 285.90 millivolt, and for that you will get the similar results in the previous section. That will be divided by 1 kilo ohm, and stop simulation is 285.90. Okay, 285.90 millivolt divided by 1000, that's almost 0.2859 milliampere, 0.2859 milliampere. Almost it is on the microampere range. It's a milli in the previous section. That's been divided by again 1000. Okay, and that can be divided by 1000 again. And so 28.59 microampere, or you can say just 285.90 microampere. So that's gonna be the answer. Okay, so what's the maximum frequency?